Hello, good afternoon, everyone. Thank you for this opportunity to present to the national labs. So in this sub-project, I want to talk about optimization of lattice structures using homogenization based on a granular micromechanics approach. So lattice structures have been used a lot for additively manufactured materials because they can be easily manufactured using additive methods rather than conventional methods. And in particular, they have been used for applications such as a high strength to weight ratio, high energy dissipation, having producing certain wave propagation behavior, like tuning the wave propagation behavior, and also in keeping with the theme of this proposal, they have also been used for sequestration of carbon, especially with respect to foam-based lattice materials. Now, the mechanical behavior of the lattice structures is what I want to talk about. And that behavior depends on a lot of the features all across from atomic scale all the way to the macro scale. So at the macro scale, we see a homogeneous material, which is actually made up of a certain microstructure. In this case, I just used a hexagonal one. And this microstructure is this unit cell of this lattice is made of individual struts, and within each struts, if it is metal, for example, we can have a grain structure, and within each grain we have atoms, and they might be arranged in a certain crystal orientation with atomic scale defects. So the mechanical behavior will depend on all of these scales. But in this project, I want to focus on the effect of this lattice design. So as we know, lattice materials can be used to span some of the empty spaces in or sparsely populated spaces in an Ashby chart, especially where your density is quite low, but the strength is still high. So you can see some lattice structures here. So like I mentioned before, we can tune both microstructure and architecture. In this project, I want to focus on architecture. And we are using homogenization, where we are converting this microstructured material into a homogeneous material. So the advantage I want to mention is, as compared to the conventionally used finite element modeling, the homogenization is based on micromechanics, and it gives us a closed form solution, which offers a number of advantages, like reducing computational time, and also making it much more amenable for optimization. So I will not go through the entire process, except that the key in this method is to connect the macroscopic deformation to the deformation of individual struts. And the way we are doing this is that we first consider this as a mechanism. We consider the lattice as a mechanism. And for a mechanism, using geometric compatibility, we can obtain the relative rotations in terms of the macroscopically applied boundary strain. And there will not be any individual member stretches. There will be only relative rotation. So this is one extreme case. This is a very soft, actually zero stiffness case. The other extreme is where the macroscopically applied strain is uniformly imposed on the lattice. That is the affine case. And by a linear interpolation between these two cases, we are able to get a good prediction using a strain tensor. Now, this I'm just showing for the example of a hexagon lattice. And If we look at the affine approximation, as I mentioned, the micromechanics method predicts a very overly stiff material. But whereas if we use the non-affine approach that I developed here, it is much closer to the finite element method. So in this particular sub-project, the ideas that I am thinking of are extending this algorithm to develop an optimization procedure to connect the lattice geometry to target mechanical properties. Right now, what we have done is for a plane stress condition in the elastic range, we want to extend it beyond the elastic range, extend it to 3D lattices, introduce material heterogeneity, because that is a very useful way to tune the mechanical properties, as we also find in natural materials, grading the mechanical properties within the material of the individual struts. Also, this procedure can interface with machine learning once we generate sufficient number of results. And also it interfaces with green engineering, as I have mentioned before, because it can be used to develop materials with large surface area, which can be used for carbon sequestration. And it can also interface with the experiments which could be done as part of the overall STEAM proposal. Thank you.